In the last video, we went ahead and derived the two differential equations that we intend to use for our simulation of distillation over time. So in this video, we're going to start simulating, which is kind of cool. So this is something that is undoubtedly a task. So I expect to make quite a couple mistakes here as we go, but I think it'll be really cool to see the final results of this video in the next. So uh, these two are um, great partners for each other, and hopefully we can learn some simulation and some Python syntax here together. So part B describes the column that we've already had, gives us a feed molar flow rate as well as a fraction of the component, an alpha value 2, and it says that we have a liquid flow via overflow at the rate equal to our Francis-Weir equation, where our W constant is 12. And we also are given how much holdup we're going to have at each stage. It's 1/10 of our constant. Oh, excuse me, it's 1/10 of our constant. So it says the trays are filled initially with feed liquid at a holdup to yield liquid flows consistent with a distillate flow rate of 0.6 at a reflux ratio of 1. What does all that mean? We'll look at it in just a second. And condenser and the reboiler are filled with a liquid at holdups equal to 10 times the holdup in the rectifying and stripping section columns respectively. We're going to assume that the condenser does that perfectly, and we have a controller on the reboiler. So let's go ahead and simulate the time response of compositions and holdups over 500 seconds. As feed comes into the column, obviously, hopefully our product composition will get a little bit more pure, and we'll be able to produce some good stuff here. What's neat about this is we get to see how long it's going to really take to make the column run efficiently. Again, this isn't really that interesting of an example in my opinion because the relative volatility of these two components is so high. Obviously, if you're in something like a refinery, relative volatility between something might separate. In terms of like isobutane and butane might be much lower, and that would really affect the system. And maybe I'll jump into that a little bit if I, you know, don't want to destroy myself by the end of this simulation. So stick with me here. We're going to figure this out. First, let's talk a little bit about a couple of these terms that I didn't really define in the last video. First off, we just have some givens here with F, Z, relative volatility, of course, I'm going to call alpha. And then we're given an L equation here. Holdup is going to be a function of N. Trays are filled throughout initially with the feed. So we're given a D here, 0.6 moles per second. And then we're also given a reflux ratio of 1. Of course, that's going to be L naught over D. We defined that in the last video. That implies that our L naught value is going to be 0.6 moles per second. Okay. Condenser and reboiler are also filled with a feed liquid at an initial holdups equal to 10 times the holdup in the rectifying and stripping section. Obviously, for the condenser, we would just say that holdup equals 12, right? Because we're assuming it's perfectly controlled. However, for the um, sorry, for the um, reboiler. Wow, couldn't come up with that word. Uh, we're using a proportional controller, so KC, and we're given our KC value, and we're going to say hold up minus, so KC times error, right, um, is going to give us our um, new value, basically as a function of time. So we have to keep that in mind when we're dealing with a reboiler here. Boiler hold up. Yeah. So what we should have, well, let's just write this out because otherwise I might mix up my variables here. So our bottoms flow rate is likely what we're going to control here, right? And so that's going to be our bottoms flow rate is going to be equal to, well, whatever our bottoms flow rate was at the time before plus Kc times our air value here. Our air value is going to be hold up minus our constant, which is 10 times hold up not. I should really write it hold up not, probably. Had that problem in the last video too. Okay, so then that's where we hit. Simulate time response over 500 seconds. So yeah, let's go ahead and attempt to jump into Colab here. Give us a new notebook. All right, so here we go. Let's go ahead and start with our imports here. So where are we going to go ahead and import? We should import NumPy, probably always. We're going to need a differential equation solver. So for that, we're going to import scipy.integrate. Solve IVP. It might be optimized. Actually, now that I'm thinking about it, let's see if it runs. Oh, it is integrate for me. And then from Lotley dot subplots import make subplots. Okay, so there are all of our imports. Coding. I'm going to go slow so that hopefully I can get this right. So what do we have? We're given a couple of givens, right? So we're given our F, where our feed rate value is 1 mole per second. We know our alpha value is 2. We know our Z value, which is the composition of our feed, is 0.5. In terms of the more volatile component, we know our distillate value is 0.6. Distillate value is 0.6. Okay, that worked. We can say that our bottoms then, right, by mass balance are going to be what? Distillate minus feed. Okay, what else do we have? Let's look at our problem statement again here. We have a reflux value of 1. So then we can say that our L from the condenser is going to be what? Reflux times distillate. Yeah. Okay. We also have a volumetric flow rate value of 9. Okay. We have how many trays are in our distillation column. Our W constant 12, and our holdup. Right? Okay. So from this, what do we want to do? We can start doing some of our basic calculations, I guess, in here, along with our L condenser. Actually, bring this down. We want to have our mass flow rate of the condenser. Sorry, molar holdup of the condenser. So what is that going to be? Well, we said each molar holdup is going to be what comes in minus what goes out, or we said we could define it by the Francis-Weir equation. And again, the way to do that, let's go ahead and solve the equation here for mass holdup, because we know the liquid flow rate. So generally, we said L is equal to W times basically Mn minus M naught. We're going to solve for Mn, and Mn here is M condenser. So maybe I'll rename this later to better fit into our array. But right now I'm going to keep it as the condenser because it helps me to remember what we're talking about. So again, manipulation by algebra, we would say L condenser divided by our Francis-Weir constant. And then we were 2 to 3/2 power, so we're going to make that to the 2/3 power. And then I think we would add, because it was minus molar holdup. Check that. Yeah. Minus molar holdup. Perfect. So now let's do basically the same thing for the reboiler, except we're going to use the Q term, which is our feed fraction. Now it's coming back. Okay. So L reb is going to be our reboiler. That's going to be whatever liquid came off of the condenser is going to flow all the way down, plus whatever is coming from the feed, right? So that was our Q is our liquid portion of the feed. Now, mass of the reboiler, not mass, molar holdup. Every time I type M, my brain just goes to mass, but that is not at all true. So what would this be? Again, this is going to be the same thing, except we're going to use L reboiler, right? Instead of L condenser. Hopefully I have this algebra right. Plus M naught as our regular flow in the tray. Okay, what else do we have? We have our vapor of the condenser. What's that going to be? That is going to be the vapor going into the condenser is going to be the same as V naught, right? So it's going to be the same as the liquid coming out of the condenser plus the distillate flow rate, both of which we define now. So let's also then define the vapor of the reboiler, which should be the liquid going into the reboiler. Well, we could define it as either one of these, actually. We could define it based on the vapor coming from the condenser, or we could say the liquid going into the reboiler. I am going to use the vapor coming from the condenser in this case, simply because that is the way we defined the liquid going into the reboiler right on this line. So let's call it the vapor from the condenser plus what? what's coming out of the feed. Right. Something's wrong here. This is vapor component of the feed. Vapor of the condenser. There should be a minus sign. Right. There we go. Now, let's go ahead and create our arrays here. So initially, what do we have? We have compositions equal to z. So let's go ahead and define that. We'll say that xi is going to be a full array of zeros, or sorry, not zeros, these. And similarly, what's going to be our mass? Well, our mass should be what? It should be, well, wait. Should be condenser all the way down to the reboiler. So it should technically have 8 stages, I think. Maybe only 7. Let's go ahead and count them here. Condenser, 2. Should only have 7. Okay. I think the easiest way to do this is going to be to row concatenate. Let's see if I get all this right. Okay. So we should have what's coming, what's in the condenser, right? So this should be 10 times molar hold up. We could have also just put 12 there, right? Then what else? Well, should actually be what? There should be M condenser, and then M condenser, because this really isn't the condenser. This is all of the rectifying section, isn't it? Let's actually call it that. Let's call this stripping. Oh shoot. That should be L rec will be M rec will be L will be L strip. This will be M strip. Decondenser. This should be the vapor in the rectifying section. This should be the vapor. Oh no. Vapor in the stripping section. Perfect. So then it should be what? M strip, M strip, M strip, because the feeding should have the liquid in the tray itself, right? It's going to have liquid hold up of the stripping section. And then N times M strip. Perfect. I guess we'll see if that's right here. Well, it's going to be size 7. I just typed in 7 different things. Okay. So we've done it. Now what we need to do is set up our differential equations. So usually we define this as right-hand side class. So that's what I'm going to go ahead and do here. Perfect. So let's see. This is going to go ahead and be the right-hand side function. And the reason I'm defining it as that is so that it's just the right-hand side of our differential equations. I'm going to input this as a vector. And yes, I think that should be for now. So let's split our vector into x and m. Should we just split back, right, into the components? Perfect. Y then is going to be x times alpha, right? Because Raoult's law over what, 1 plus x times alpha, something like that. I'm pretty sure it's that. Yeah. Let's look at Raoult's law alpha. So there should be a 1 minus in there. 1 minus x plus x times alpha. That looks right. dm. I'm going to go ahead and define this then. dm will just be my matrix of m's. Oh. And the reason I'm calling it dm is just to differentiate it from the m we just had above. And that way I can just define it exactly like we defined our differential equation here, right? Right. So let's define this as zeros like m, right? And then we can do one for x as well. I'm going to call it dmx so that I remember to do the product rule at the end. And here's x, here's like m, whatever. It doesn't really matter. We can do it like x for now, though. Now let's define what else do we want to define? I think liquid from each. I feel like I'm missing something here. Here is like m, and vapor is going to be zeros like m. Okay, let's keep going. We have to figure out what we skipped when we get there. Okay, so we set up our arrays, but right now there's just zeros in there. What we need now is okay. Yes. Let's go ahead and find our initial liquid. So this is going to be the liquid in the condenser, right? We can just define it exactly the same way as we did above. Let's do the same then for the rectifying is going to be R times dE plus D, right? So how do we define it above? Well, right now we're not focusing on Francis Weir as much now, right? Because this is just supposed to be generally for the section. B equals dripping equals the rectifying minus liquid times B. Okay. Then let's go ahead and do vapor here. What do we want to concatenate? We want to do vapor going out of the top stage. So top stage we're calling guess the condenser, right? Because we already defined L naught as what's coming out of the condenser. So 0 out of the top. And then we have V rect V rect V rect. And then we have V strip V strip V strip. Perfect. Now we've done all of our vapor. Let's look at our liquid here. Liquid, basically everything except for what's coming out of the condenser is what we want to define. We're going to go ahead and do this basically by using that hold-up equation, right? The Francis Weir equation. So again, what do? We say W times M well, I guess we want to index it the same way, Mn, right, minus M naught to the 3/2 power. See if that works. If I have enough parentheses in there. It doesn't look like there's anywhere else to put them. Okay, is that everything to really set this up so that we can start finding our DMs? Let me look at the problem statement real quick. It says razor filled with hold up to yield liquid flows consistent with the distillate flow rate, the ratio of that. We defined all that. Initial hold up is equal to 10 times. We did that in the condenser and the reboiler. We need the proportional controller now in our reboiler. So we defined our initial hold up earlier, but let's go ahead and do it for the reboiler. So I'm just going to go ahead and put KC in, and then we're just going to use the equation we wrote right here. So I'm going to say, what do we want to call this? Bottoms flow rate equals B naught I did define it as B earlier. That's why I'm struggling here for a good name. B, call it B1 for now. I don't have a good one. Sorry. It's probably terrible variable naming, and I'm probably going to get confused in a second. Let's do KC times error, and our error is going to be, what is it going to be? It's going to be, what is the molar holdup on the reboiler stage, which would be molar holdup on stage 7. Let's just make it the last stage to keep it clear. Minus 10 times molar holdup, because again, that's our set point, right? Okay, so I think that's that. Let's say I feel like I remember in class. Well, I don't know. Let's just put L1 equals 1. Sorry, L negative 1. My bad. Should be 1, right? Awesome. So now we can start to define our differential equations. So dm, we're going to do this exactly as we did on our paper here, except instead of using in, we have to use Python indexing, which might kill me. So this is the part where I have to go real slow. Let's start with our middle stages here. It's going to be what? It's going to be the vapor from the stage above, no, below. Vapor from the stage below. So 2 onward. Plus the liquid from the stage above. Stage above is going to be what? 0 to -2 plus, or rather minus vapor from this stage minus the liquid leaving from this stage. Awesome. Now for stage 3, let's go ahead, because this is the feed stage, right? Let's make it DM3 plus F. So then we're just adding what's coming in from the feed, right? Okay, so now I defined these in the last video. Our reboiler and our condenser. Let's try this out here. Not feeling super confident, but we're gonna go for it. Condenser. We said that was equal to, let me pull this up real quick from last video. We said condenser is going to be equal to D1 plus D1 minus D minus L naught. So let's do it. We're going to say D1 minus D minus L naught. Then dm -1 be equal to L from the last stage, stage 6, the second to last stage. Yeah, there we go. Okay. Minus L -1 minus B from the last stage. Solid. Now let's do dmx. Let's see. Actually, let's start with dx and hope that this would work for matrices. So dmx minus what? X times dm divided by m is going to give me my x. So let's define our dmx here. Dmx from 1 to -1 is going to be equal to all of this multiplied by its corresponding composition. So for vapor, it's going to be y to the n. For liquid, it's going to be x 0 to -2 times y 1 to -1 times x 1 to -1 times a. Now we need feed stage here. So this guy. Just multiply that by z. Now dmx 0 is going to be this all multiplied by its correct compositions. So distillate, remember we are using a total condenser, so our distillate is going to be a liquid here and not a vapor. And then This should be a distillate. This should be liquid. Well, perfect. And then our reboiler here. So again, at 2 time, and then another liquid, 1 and another vapor. Okay. Now, what do we want to return? dm and dx, right? Return. How do I want to stack them together, though, is the question. Hold up, I try and remember. I think it was just a row concatenation. It would just be dm dx, or opposite of what I said completely. Okay, so that's our function. We've done it. Now the question is, can we plot it? It's a great question. Let's run it. So t end of our simulation is going to be 500 seconds. Whole VP. Our function is right hand side. Would want to do basically just over any t. So let's call it lambda t vet. Our vector function is going to be right hand side t vet 1 from 0 to t end is our time span, and then we want to put in a row concatenation here from xi to mi. That's our initial conditions that we were supplied. Method is going to be redo, and we want to make our dense output. Dense output equal to. Cool. Now, what do we want to do? T-plot is going to be lin space. What do we want to run? 50 points. Let's go res1, res sol over t-plot. Then what else do we want to do? We need to split this into two solutions here. So x1, well, how do I do this? Just call them x and m again. Just call it x's and m's. Equals, we want to split our res1 vector 2 times. Axis 0. Great. So let's plot it now. Big equals make subplots. We're going to need another column now. Then how do we plot this? Hold up. I'm going to have to. Okay, so what we want to do is a for loop for I x m, then enumerate the x's, yeah, x's m's. What we're going to do is we're going to add our x's to one plot, I'm going to add it to the first plot, and give it a name here, f string x. Basically do the same thing, put it on the second plot, and make it m, and make it m. And run. We want to go ahead and make this an input as well. Not running our solve IVP. So I think what's happening is, I was kind of worried about this, that our B1 is returning 0 values or negative values. So obviously that can't really happen. So let's go ahead and put an if statement here. B1 if B1 is greater than 0. We can say else. Let's just put in 0. Still getting zeros in here. Look at this. I wonder if I should put some extra dots down here. Sometimes they'll get you. Okay, still not running, but we'll get it there. We'll get it there. Let's look at I'll take it off. I think all these times I have zeros in front, I don't technically need those. Which array is it? Some array is getting 0 values in it, and that's what's screwing up the code here. Question is, which array is it? Maybe I should define this as r times a and not call in our other value here. We can do that up here too. Or do it before. Well, not like this. R times D. Oh, should be a D there. There it runs. Okay, well it's indeed run and then not plot anything, so that's nice. Huh. Big dot show or something adding here. Um, so 700 height equals 400. Input equals aha. Okay, so we got a plot. It is not correct. As we would not expect our M to go so high, right? We should expect them to start to obtain some steady state after some time here. So let's go ahead and see where we went wrong. Okay. Well, it should be DMX. DMX. That's going to be a big piece. But I didn't have some DMXs there. Let's see what that changes. Okay, so now we're in the right spot in terms of this graph. Because again, we're hitting steady state fairly quickly, honestly, with our two outliers obviously being our reboiler and our condenser. Of course, the reason for this, again, this is the hold up graph. Reboiler and condenser should be much higher than the rest of them, right? They should be 10 times. And the reboiler has a control that perhaps is making it a little bit closer to exactly 10 times 12.53 compared to 1.33. Well, again, this should be 12.0 really, right? So you can see it dropped it, whereas I'm not, or the pull up and the controller is not doing that well. Let's see if I can find any other guys in here that are not as quick. Let's try and make this into a plus equals and see what that does. Still nothing there. Yeah, that's times. That all looks right. Troubleshooting code. Oh, I think I see it. Because this has a minus in it, and this has two minuses. This should really be a plus. Gotcha. Okay. Zoom in here to get a closer peek at these. Okay, So we can see how composition of each tray changes, specifically how composition of the more volatile component changes. As you would expect, the higher the tray, the higher the composition of the more volatile component, right? So 1, 0 through 7, or 6, I guess, with 6 being the reboiler. Well, I used -1 instead of 7 because we didn't actually have 7 indexes because of Python's indexing, right? And so here's our feed stage. You can see once we switch from rectifying to stripping, we kind of get those curves start trending downward instead of upward. All right, that's simulating over 500 seconds. In the next video, I think what we get to do is implement a reflux ratio change and see how that really manipulates the composition of our products and how they change over time. I'll see you in that one. Bye-bye.